Good night and welcome back to Fundamentals of Engineering with Farhad. Mechanics of Materials, Axial Elongation. In this example, we have like a tapered cone handling a concentrated load of P applied at the A. The length of or the height of the tapered cone is L, and we want to calculate delta at A due to this concentrated load. Let's approach our problem. So we have like axial elongation in a variable cross section, like what you can see here. We just flip-flop, we rotate our tapered cone by 90 degrees and then analyze it. The concentrated load applies at the end A, and if we just consider like extend it all the way through the point of origin, we just create it, and now we have a full cone. And then if we call the A and A to the origin like L sub A, and B L sub B, and then create just an element for our case by the length of X somewhere in the middle of A and B. Then we call their diameter like D sub A, D sub B, and definitely the middle element is dx. Then if we just jump to the relation between the length from the origins and the diameters, it just says LA to LB is related to their diameters, dA over dB. And likewise, if we do the same for diameter of the element X, dx over dA is like the distance of X over the LA. Then we can have like a differential form for dx for our element. Like the diameter of X is x dA over LA. Then A sub X is equal to pi dx squared over 4. And if you just simply replace dx from this equation to equation of A sub X, it just gives us A sub X is equal to pi dA squared x squared over 4LA squared. Then if we have our variable air cross section area by this function, then we can easily jot down the equation of delta, which is the integration of nx dx over EAX. So for our case, delta is the integration from LA to LB, then replace N by P because the force is just a concentrated load, P dx times 4LA squared. We just replace AX in the equation over E pi dA squared x squared. And as you can see in this equation, only dx and x squared are the variables. So we can take all the constant out of integration, and then you can have like delta is 4 times p times LA squared over PEDA squared, then integration of LA to LB dx over x squared. And if you do so, it just says delta is equal to the constant times the result of this integration is a negative 1 over x from LA to LB. If you replace the numeric value in our integration limits, it just says this is our delta. And definitely the part in bracket is if you just simplify the mass, it just says 1 over LA minus 1 over LB. It's just L over LA LB, because based off problem statement, the distance or the height of our tapered cone is LB minus LA, and that's L if you remember from the problem statement. So we just replace it here. And then delta is nothing but 4 times P times LA squared over in denominator pi EDA squared. Then multiply by L in numerator and LALB in denominator. It just comes from here. And then if you cancel out one of those LA in numerator with the denominator, and then we do know that the length of A over length of B is equal to a diameter of A over diameter of B. Then delta is 4 times P times L over pi times E times dA times dB. So delta A in a tapered cone by a concentrated load of P, delta A is 4 times P times L over pi times E dA dB. Thank you. We'll solve more problems.